Jacob Cooper, and this is my Physics 2211 Lab 2, the motion of a falling object. A little bit of an intro here. So the purpose here is to observe the motion of an object that is dropped from rest. In this presentation, our object's a paper ball. We're going to observe the motion in a tracker program, and then we're going to use some of that data to input into a GlowScript coding. And then we're going to kind of compare the models between our experimental model, and then our models considering gravity, and then gravity and drag. And ultimately, we're trying to demonstrate the principles of Newton's second law and some effects of gravity and drag. Some key formulas: we have our velocity update formula right here, our position update formula, our force due to gravity, and our drag force, which we will implement these in a couple slides. Here's our video, short and sweet. And so here's our coding portion for just gravity. We're not considering drag here. So the mass of our ball, 0.01 kilograms. Our position and velocity vectors initially starting at 0, time at 0. We have our gravity constant, which is 9.8 meters per second squared, a unit vector. And then since we're not considering any drag, b is 0. And then over here we have our velocity update and position update formulas, as you can see, getting implemented. And then our net force, we're using the gravitational force formula. And then here's our code sample from considering gravity and drag. So really the main differences is that we have a proportionality constant, which we got using trial and error to best match our experimental model. We have our while loop set to the time less than or equal to. And we have a couple key differences here. So instead of just using our net force as with the force of gravity, we are also going to consider the drag. And that's our formula there, the magnitude of velocity squared times b times our unit vector. And then here's the same formulas from earlier. So here's our graph here. We have the observed, the no drag, and with drag. As you can see, our two models with drag kind of are a bit more upwards than our one with no drag, and which just makes perfect sense because drag is obviously going to slow it down. What does it mean? So our question here, what does it mean, is what does terminal velocity mean? And terminal velocity is just when the force of drag balances out with the force of gravity. And so here we have no terminal velocity, but here, as you can see, as we get a little more downward, you can see maybe we may have reached terminal velocity. I can't say for sure, but can't say that terminal velocity you're going to see start with there's really going to be no more change in acceleration, and your graph's going to look a lot more linear. I can't say for sure on ours. And then our what if just being, what if the object was initially thrown downward, and so would it be any different? And the answer is no, it wouldn't be any different, because the terminal velocity would be the same. The only thing that would be different is maybe it would reach terminal velocity faster rate. And we proved it with our code. So we skewed the numbers, and our graph looks about the exact same. At least our line here. Potential errors could be errors in tracker, and also errors with the drag constant that we use in our code. And yeah, thank you.